afternoon. This is SI Sasha Nasinovsky. Today we're going to look at this problem involving critical angles and refraction. So, let's read it off. You can determine the index of refraction of a substance by determining its critical angle. What is the index of refraction of a substance that has a critical angle of 68.4 degrees when it's immersed in water? So we'll tackle the water part first. When it comes to critical angles, this is essentially what we're looking at. So say I have a boundary, something like this, or maybe a little straighter than that, and we have one index here, and indices just refer to the speed of light and how it changes. So we have this index here and this index here. We have a formula that says the sine of the critical angle is equal to the division of this top index over this bottom index, n2 over n1, specifically for when n1, index 1, is greater than index 2, okay? So what we're being told right now is that the index we're looking at, whatever it is submerged in water, which means that this index right here above must be water, so it must be 1.333 from our table. And we're solving for n1. We don't know what this substance is. All we know is that the critical angle is such that when I have an incident angle from the normal, let me draw the normal real quick, say this is the normal here, when my incident angle of the light coming through like this is theta equals 68.4 degrees, I know that when this light reaches this boundary, it will not refract through anymore. It will refract such that it just continues along the boundary like that. Okay, and our formula tells us, well, if we know the critical angle and we know this top index or the bottom index, we can predict what the other index of refraction, if unknown, is. So let's do it. We know that we're given 68.4 degrees. Sine of 68.4 is equal to 1.333, our index of refraction for water, over some index that we're not aware of. And then to solve for n1, we say 1.333 over sine of 68.4, which evaluates to just about 1.43. If we reference our table, that looks suspiciously similar to fluoride, which is 1.434. So what do we know? We know that this is probably referring to fluoride. So whatever our substance underwater is, N1 is fluoride. Okay. And the next part asks, what would be the critical angle for this substance if it were immersed in air? So in other words, what we're doing is we're saying, okay, same situation. We know, we know N1 is 1.434 fluoride, and we know N2 is equal to 1.000, I think it was like 9, but we can just keep it as 1 for simplicity's sake. So here we have air, here we have fluoride, and we're now solving for the angle such that when this light does this, some unknown theta here between the normal and this light, the light travels up and never even refracts out of the boundary. It goes along the boundary and it never crosses into N2. So how do we solve? Well, we once again refer to that formula. Sine of the critical angle, which we're solving for, is equal to, well, what do we have? 1.000 over 1.434. And if we solve for that, we get sine inverse of 1 over 1.44 is equal to theta critical. And we get theta critical is equal to just about 44.2147 degrees. So we know this theta right here is equal to, well, that, right? There we go. that's that problem. It's not bad. This is mainly about recognizing the formula you're working with. In this case, we're discussing critical angles. Then it's talking about, well, we are given an index. Like in this case, we're given that the index of our boundary up here, this top index is water, um, and this bottom one is unknown. So once we solve for our index for n1, we then say, all right, forget about water, let n2 be air, and just replace the top n2 right here with 1 and solve for the angle. And it's a relatively simple problem. It is, again, just about consulting the table and knowing what to do when faced with specific keywords. Definitely refer to this formula when you have anything to do with critical angles.